Hi, so today I'm going to talk about paraffin wax, which is more commonly known as candle wax. So these are my bulk scale pictures. This is my substance when the candle is lit, and this is what my substance looks like when the candle isn't lit. My researchable question is, how does the molecular structure of paraffin wax allow it to act as a fuel for the candle? My bulk scale properties, and you can look at this picture of a candle that I took for reference, is that it's solid at room temperature and liquid at higher temperatures, it's water repellent, and it has a smooth texture, low toxicity, and little odor. My molecular scale properties are, so paraffin wax consists of a hydrocarbon makeup, which means that there's varying amounts of hydrogen and carbon atoms present in the molecule, and you can look at this equation CnH2n plus 2 as reference. It's an alkane, and the most relevant information that you need to get from it is that there's twice as many hydrogen as carbon. There's chains of carbon atoms that are connected and they're surrounded by hydrogen atoms. The carbon to carbon and carbon to hydrogen are bonded covalently, which means that they are very strong. The chain itself is short and flexible, and there are weak IMFs bonding um, two molecules together. So this is my model, and you can see over here how I labeled one paraffin wax molecule looks like this. So there's a hydrogen atom, which is shown as the blue, a covalent bond, which is shown as the black, and a carbon atom, which is shown as the green. And you can see how this chain, it doesn't go like straight, it's down, up, and that's what I mean by saying that it's flexible. You can see in this zoom in bubble how multiple paraffin wax molecules are bonded and what it looks like. Recall that there's weak IMFs bonding two molecules together. So my CR, recall that my question was, how does the molecular structure of paraffin wax allow it to act as a fuel for the candle? My claim is that the hydrocarbon makeup found in paraffin wax allows it to act as a fuel for the candle. My evidence is basically everything in my molecular scale properties, and my reasoning is, when a candle is first lit, the heat from the flame melts the wax near the wick, and this doesn't require that much time or energy because there are weak IMFs um, connecting paraffin wax molecules together, and that makes it easier for them to separate. Then the liquid wax climbs up to the flame by capillary action via the wick. And if you look at this picture for a second, this is the wax, this is the wick, and this is the flame. And the chemical reaction takes place in this bluish part of the flame because there's more oxygen present there when compared to here. And so the flame continues to vaporize the liquid wax, which means that it converts it into a hot gas, and it starts to break down the hydrocarbon into separate molecules of hydrogen and carbon. Recall that this takes a little more time and energy because these molecules are bonded covalently. Now, in the flame, these vaporized molecules react with the oxygen present in the atmosphere to create heat, light, water vapor, which is H2O, and carbon dioxide, which is CO2. This chemical reaction is known as combustion, and it produces enough heat to melt more wax near the wick and keep this process going until either the fuel gets used up or the heat is extinguished. Basically, what I'm trying to say is that this process is self-sustaining, and this is how the paraffin wax acts as a fuel. Now these are my works cited. 1, 2. Now this website was experiencing some technical difficulties, so I wasn't able to cite it in MLA, but it's a very reliable source and all other information is here. 3, 4, and 5. Thank you so much, and I hope you enjoyed my presentation.